I got inspired by this post on Pinterest and decided to make an animated version of it using geometry nodes in Blender. Instead, I ended up building a system to easily make a variety of similar designs, and today I'm very excited to share its inner workings with you. The basic idea is to generate 2 splines for every polygon of a mesh, each one covering one part of its circumference. Then connect the control points of those splines with 2-point crossing beams and slide them along the segment curves to create a mesmerizing effect. This system is super versatile and works well with n-sided polygons, making it ridiculously easy to create all kinds of moving tiling patterns. Let's now build it step by step. Start with a mesh grid, an easily subdividable geometric primitive. Split the edges to work with each polygon separately. To see those polygons clearly, scale the faces using a Scale Elements node. Now convert the edges to curves. These are the outlines we're going to work with. There are different ways to generate curves that lay on top of other curves, but trimming is the first that comes to mind. Append a Trim Curve node immediately after. The ability to trim cyclic curves is a new feature of Blender. It works great in this case because all our splines are cyclic. Anyway, we need to generate 2 curves, the first one covering one section of the original and the second covering the rest. Connect a value node at the start input. The end of the section will have to be equal or greater, so add something to the start value and connect the sum to the end input of the trim node. To have this segment loop around, insert a fraction node before the start and end. A fraction function is the same as a modulo of 1, but it works with negative values too. The rest of the length will be covered by a second spline, which will generate using another trim node. This section will start where the previous one ends and end where the other starts. So cross-connect both inputs. Let's now tie these section curves with 2-point beams. Resample both sections with the same point count. Start low for now. Append an Instance on Points node to the first one. A curve line is what we'll instance. This generates a 2-point curve, which is exactly what we need. Right now, those instances are positioned at the points of the first section curve, but they are pointing straight up in the Z direction. To have them point at their counterparts on the other section curve, we need to sample their position vectors first. Now, because both curves have the same number of points, we can get the position vectors based on the index number. Add a sample index node to the other curve. Change the data type to vector and the domain to points. This returns the point positions of the other curve. To get a direction vector for each instance to point to, subtract the position vectors of the first curve from the position vectors of this one. Then, convert these direction vectors to Euler rotation vectors expressed in radians using an Align Euler to Vector node. Feed those subtraction result to the vector input and choose the z-axis for the alignment. The result will rotate each instance toward the point with the matching index number on the other segment curve. It may look like a mess because the instances have the same length. We'll take care of that in a moment. We already calculated the direction vectors. Now let's get their length and scale the instances by that value. Remember, this works correctly because we're instancing 2-point curves, and scaling them equally on all axes will only affect their length. A problem that rises is the direction of the segment curves. Because the second one starts where the first ends, the beams are crossed indeed. To remedy that, we simply reverse the direction of the second segment before the resample takes place. This corrects the direction of the beams. Raise or lower the beam count as you need. You can also expand or shorten the segment length or even slide it around the original curve and make it cover another section. What remains is to animate the beams around. For that we need to slide both start and end points of the beams along the section curves. Insert the set position node before the instancing takes place. We'll slide these points along the trimmed section using a sample curve. Because we're working with many segment curves simultaneously, we need to specify a curve index. A simple index node won't do in this case because the set position node works on points, so the point index will mess up the calculations. Instead, we'll evaluate the index numbers on the spline domain. Right now the beams are bundled at the same point on the segment because we're feeding them the same factor value. To spread them equally along the curve, divide the index number of each spline control point by the total point count. Remember, we're working on many splines at once, so instead of a simple index node, we'll use a spline parameter together with a spline length node to get the indices and the point count. Dividing the index by the count number will return a value from 0 to 1. Append a fraction node to have the sampling factor loop around. Before moving on, duplicate both set position and sample curves. Hold in Ctrl plus Shift D and replace both geometry inputs and outputs so that the same shift is applied to the other segment curve. Now, insert an add node before the fraction function. To keep the video short, I'll animate this value with a simple expression driver. Type #frame divided by 300. This will complete a full loop in 300 frames. Hit play and proudly watch the result. Don't forget to bundle the nodes in frames and rename them after the function they do. It will be very useful to decode your node tree later on. You can further add to the setup. For example, you could randomize the sections covered by the sliding curves. Simply add a float number with a range from 0 to 1 to the initial trimming value. Experiment with different seed numbers till you're happy with the result. You could also animate the start value, the same as we did earlier, to have both segments slide together along with the beams. Join the beam curves with the original outlines to get a better picture. You can also group the nodes, expose the needed parameters, and add that group to your assets for later use. This setup is fully procedural and will work with any polygon, no matter the point count. Using it, I was able to quickly iterate through different versions of these tiling geometries. I tried to keep the video short and hope to have explained everything clearly. In any case, you can rewatch it. If you have any questions regarding this technique or come up with a shorter way to get the same result, feel free to comment. And as always, if you like the video, please share the knowledge.